All right, good morning. We have 20. Oops. Oh, hey. Oh. It's today. Today's the test. Hey, it's down to 0.
We told you we want
He also didn't have his probe. There we go. It'd be funny if like a different number's behind it too. We're not ready to. All right, we are gonna finish up talking about what we started yesterday, which was precipitation, and then we're gonna get into just the beginning of some other material. You should have that note sheet ready to go. We'll talk about the worksheet as well. Okay, so this is where we left off yesterday. And basically this one's, of the three, I think is the most confusing one. And usually it bridges barely into this, but I wanted to talk about the different kinds of precipitation problems that you could have. So yeah, we mixed two different solutions together. It said find the concentrations at equilibrium. Well, we found out that a precipitate forms, okay? So once we know that a precipitate forms, this is where we are at then. Is that we are talking about this equation. Okay? And what we are saying is that if a precipitate forms, what we just realized is that it shifts back this way because it's going to make a precipitate. So now we need to apply some material to that, okay? So what I need to do is now an ice box. I'm going to plug in the numbers that I have, and I already have them kind of right here. So from the magnesium, magnesium nitrate, I have 150 mils and 1 × 10⁻² molar. So I need to find out the number of moles of each of these. And I just bled in there a little bit. And then the fluoride, I have 250 mils. The whole point, I want to find how much I have of each. Okay? I have 1.5 millimoles of Mg. I have 25 millimoles of F-. And what I figured out was I have too much of this. It needs to come back this way. And if you're, wait, how did we find that out? I compared it all. And you need to be setting this up because this is the math. This is how we're going to work this out. Okay? So it's going to shift this way. So if that's the case, so you understand, then that's going to be minus x. And this is minus 2x. Okay? Now, there's no way to get around it. This is a little bit of a confusing moment. Well, what is x? I don't get it. Because this is a solid. So I can't have anything on that side. Well then, how far do I go? I don't understand. What we're going to do is we're going to exaggerate this thing, and we're going to drive it all the way to solid, and then let it flutter back using the k. So meaning with that is I'm going to take the smallest one. I'm going to assign it 0. Again, of the three, this one is easily the most difficult of the three. The next problem, even though it sounds more difficult, there's a lot less work. So if that's the case, then x is 1.5, right? Correct? So then what is my final amount of millimoles here? It'd be 22, right? Because 1.5 times 2, right? So I'm going to have 22 millimoles right here. Okay, so I can figure this out. What do I have? 150 and 250, so that's 400 milliliters, which we've already stated once before. And I'll do the math with you a little bit here. The reason why we're going to push it back the other way, or the amount that can be pushed back the other way, it's not that we're going to run out of fluoride. We have so many more moles of fluoride, millimoles, than of magnesium. So this ran out. So right now we shoved it as far over to the side of the solid as you possibly can. So now what we're going to do, I believe we already wrote this on the board, on our notes. So you don't have to write this again if you don't want to. I just wanted to, I believe we have this from yesterday. What I need to simply do now, just like before, remember, okay, with titrations, I flood it as far over to the side and then it has to flutter back. Here, what I did is I'm forcing it as far over as I can, and then we'll just see how much kind of comes back in, because something has to dissolve. Something always has to dissolve. I can't stay at 0, okay? You cannot have a 0 in an ice box at the end. So what I can do, though, is I can plug it in now to this. So this is what I'm going to do. What's the KSP? 6.4. Is that -9? Yeah. Okay. I don't know X. Sorry, mg. I don't know mg. And then what would, if it was fluttering back now the other way, see if anybody can come up with this without me having to do another ice box. What has to go in there? It's going to flutter back now the other way again. So I pushed it all the way here, and now it just needs to redissociate so I don't have zeros. Plus 2x. It has to flutter back the other way. To be honest, this isn't going to matter. And you're like, wait, why? I mean, it does in the idea, but like, I have so much of this, it's not going to really affect it. This is going to be minuscule. It was already minuscule, and it was still too much. It was still too much because it said that it precipitated. So just a little bit of it's going to come back. So what I need to do, like always, I can cross out things that are added or subtracted. Okay? And when it's all said and done, and don't let what we are doing yesterday and then today, just because of this, the ending of this problem, kind of shift your, let's say, equilibrium of what you understand, but your feeling of ice boxes and KSPs will still be okay. This one's just a little trickier. I got this. It's very small. 2.1. You're going to help me calculate the next one, so I'm going to do this one. Times 10 to the -6th. Now, if you're like, well, okay, well, let me plug that into here. You put that in, multiply by 2, and add it to that, it's still this number. It's still the number. So, at equilibrium, that's how much is going to be there.
What is the number? 2.1?
2.1 times 10 to the -6. Sorry. Yeah, I'm kind of writing small. Apologize.
So you don't have to put the square root on the F then for the equilibrium?
No, because this is the concentration. That's a great question. The concentration and the square, this is still how much there is. It's just the relationship within the equation. Yes, like the amount is still the amount inside. All right, so I know that's a little confusing, and the fact that we did it disjointed, just kind of, I guess, keep it in perspective. What did we do? Yesterday we figured out, will this precipitate? If you found out it wouldn't precipitate, these amounts, that would be done. You put it over 400 and that's it. Oh, how much, what's the concentrations at equilibrium, meaning either it dissolved or came out of solution. Hey, it's done. They all dissolved. We found out, oh, it doesn't all dissolve. Oh, shoot. Okay, that means I gotta push it all the way as far as I can and then see how much actually will come back into solution. So it's almost like kind of taking it out of solution as solids again, pouring it back into a liquid and stirring it up, and then whatever does dissolve will. Whatever doesn't won't.
The concentration of Mg plus.
Where did I get it?
Like how?
So then I just re-plugged this in. I acted like now the equation's coming back this way. So this was my F. X is, it'll be like 0 plus X.
Mm-hmm.
So X is my Mg. This is my KSP.
Wait, is that 0.0055 or is that
0.055. 0.055. Thank you. Ooh, you're close. Okay, let's get to the last one. So then we can kind of jump into the new material here today. I think this one will click, I hope, and then maybe everything will kind of come together. Fingers crossed. Here we go. This one does not have as much work as it sounds like it's going to have. So stay with me, please. Your packet will help you a lot, though, with this as well. All right, so what I have a solution of copper and of lead. Okay? If I slowly add iodine, I'm just adding iodine in there. Which one will come out first? When iodine connects with Cu or when it comes out with Pb? And it's like, oh God, this sounds really confusing. Let's break it down and let's try to simplify it. How I simplify things, I like equations, okay? So these are the things that I'm talking about. I have CUI. Well, that could break up into this. I have PBI2. That could break up into this. The thing you don't have yet that I need to give you is the KSP of each of these solids. So let me give you that.
How are you supposed to know that? Or is that-
I have to give that to you.
Okay.
You're not in economics today. Nice.
He decided to have some brain cells.
Oh,
Wow, wow, whoa, whoa.
I'm wearing the supply and demand curve, okay?
Okay, if I just ask you which one's more soluble, is it the copper or the lead or iodine? Which one's more soluble? Brody says the iodine, or they're both iodine. You tricked me. Oh, the iodine one. Yes. Dang you. The larger the number, the more it means it shifts to the right side. So if I just asked you just point blank, without knowing any other data, which one is more soluble, it is the lead. Because this dissolves more into its ions. I hope that makes sense. Okay? But it matters how much you have of it. So we could trick the number. So this is how we're going to do this. And it doesn't need to be as complicated as it seems. Let's talk about the CUI. And the answer at the ending, I hope, will make sense. So let's just talk about CUI. What I'm going to do is I'm going to put it into the KSP relationship. Remember, at the ending of this, these numbers tell us the maximum amount that can dissolve. Keep that straight and everything will be better. It's the maximum amount that can dissolve. So I have 5.3 times 10 to the negative 12 equals Cu plus I minus. So I'm going to plug these numbers in. I have 1.0 times 10 to the negative 4 times x. This comes from the copper in the problem. I don't know how much iodine. What if I just slowly add it? What I'm going to figure out is the maximum amount . What that means, that's the maximum amount that can dissolve in the relationship to the KSP. So I get an answer of this. That's an 8. 5.3, hopefully you guys on the side, sorry. I'm trying to write as big as I can. Do the PBI2. I plug that into the KSP, and we'll continue to repeat this because this is what got me stuck when I was first learning this. I don't understand what KSP is. It's the maximum amount that can dissolve. So with both these equations, I plugged in the source of my Cu and my Pb, so then that's telling me the maximum amount of my iodine that can dissolve in there because of the amount of Pb and Cu already in there. So this is the maximum amount that can dissolve. The question is, if I slowly just keep adding iodine, which one will precipitate out first? Will all of a sudden there be too much of this combined relationship, this bond of Cu and I, or PBI2 and it'll precipitate out. Well, based on here, this is the maximum amount that can dissolve. This is the maximum amount that can dissolve. So if you're pouring at the same time, which one's going to come out first? CU or PBI? CU, because that's the least amount, right? That's when I get to that amount, then all of a sudden CUI is going to start precipitating out. This one can hold more still before it precipitates out. And I had a good wording with this. I just wrote, takes lower concentration. I hope that kind of makes sense. I thought when I did this problem just on a sheet afterwards, I'm like, you know what? I would think that would help kind of just give me a better picture in general of what this can do for me. Okay, so maybe the question just would simply be, erase one of these, and I just say, hey, how much can dissolve? Or I could say, what's the amount that it would take to start to precipitate? Well, what the answer would be then is greater than this, right? Greater than this value. Anything more than this starts to precipitate. Okay, if you can even just have that register with you. Okay, so the numbers that I get out of a KSP, that's the maximum amount. Anything more will cause it to precipitate. Anything less will stay dissolved. So we'll continue to practice this. Believe me, we will not go nearly as in depth with KSP though as like KA and KB. Like we're done. All we're doing now is practicing things like this. Like we're not gonna, okay, now we're gonna add this and that. We're gonna turn it all around. Just we're gonna be plugging them into KSP. Our job will be to recognize when we use the equations, when we have to use an icebox, and the packet actually does quite a good job with that. So if you didn't start it, I had asked you to start at least exercises 1 through 3. Hopefully you have. Okay, so all right, we're going to jump though into our other sheet, entropy notes. So please get those out. Which one naturally happens? Depends on what kind of person you are. I will not agree with that. What will naturally still happen?
Nothing.
So, I got a deck of cards. And when you first take out the deck, I don't know what's on top and what's on bottom, but it goes like from ace to king, or ace to 2, or 2 to ace, or is the ace below the 2, or is it above the king? Actually, I don't know when you first get the deck. No, when you first buy the deck. Ace 2. Okay, let's say it's ace 2, 3. So it's ace to king of each suit, right? I guarantee that if you take this deck right now and you just do that, and then I pick them right back up again, I was going to throw it this way, but then I thought it was going to be really hard to get. It would not be back in that exact same order. There are, I don't know the probability, people in AP stats or just stats, you can tell me, the probability of all the different other solutions to that, but there's only one order to put it back the way that I had it, right? There's only one scenario that goes back that way. There's countless other ones to be every other way, okay? So we have, he's got wet. Wow. We have all these other different opportunities. And I've been practicing this, but I didn't do it this year yet. And you could try to shuffle them, and as long as, come on. As long as you can hold on. No, okay. I still have more decks. So, you're going to help me out here. I'm going to shuffle this up. I'm not Mr. Lenz, but let's see what I can do. All right. Put your finger into the deck whenever you'd like. Pull out the card that you land. Okay. Okay. Pull that out. Show everybody else.
Can't see it.
Maybe don't show Rory because he'll tell you. Okay. Put it back in. Okay. All right. So we're talking about order. We're talking about finding the same exact path as possible. Here we go. Anytime you want. You got it? Pull it up. Show everybody. Show everybody. All right. Put it back in wherever you like. Okay. Okay. Okay.
When Justin is Jimmy Lance. We all thought he quit.
Rory, no, you know what? You're gonna mess this up. Jane? Anytime you want. Okay, pull it out. You can do it. Hold it. Just one card. There you go. Show everybody, please. Show everybody. Okay, see, because there's disorder, so every time we're pulling out a card, we're getting a different one. All right, every single time so far. And every time we pull out a card, it's a different card. And because there's all sorts of different kinds of possibilities. Last time. Go. Okay, pull that one out. Okay, show everybody. All right, did you show everybody? Everybody see it? Everybody see it? Okay, so we've had, what, four different cards out of 52 cards so far, right? So, obviously, there's all sorts of different possibilities. But when you create order, sometimes there is not order. What? Alright, hey, I'm here all day. So, we're going to talk about order and disorder today. If you don't know what happened, don't think about it too hard. Alright, here we go. So, entropy. Kid you not, my senior speech, I did a magic show. Because everybody else was doing like, you had to do something how-to, so everybody was like baking cookies and everything else. So I did a magic show instead. It was a horrible magic show, but I did one anyway. All right, so this is what we learned before. Kinetics is about speed. Keep up with me here. So that just, oh my gosh, it showed up. That's what I should write. Thermodynamics is about heat flow. All right, so what does that all have to do with anything? Well, the whole point of this is that we are going to truly go down the path right now. This is a mess in here. Of figuring out when something's going to react. It says, what makes all things happen? You know, it's kind of like a guessing game sometimes. You know what? We have some tools like, hey, that is higher on the activity series. I know that's going to happen. Hey, that makes a precipitate. I know that's going to react. But why do we know things are going to react and other times things won't? Well, we are entering that world right now. Why do things react and why things don't? So, this is one thing that we've said before, is that usually items try to release heat. Okay? You're trying to release it. So you have all this energy, you're trying to release that. Or you can think of it as energy goes down. Like you're trying to release that energy though. You're trying to lower that energy. I have we have certain expectations and we know certain things happen. You don't see a firework go up and all of a sudden this impulse goes in. Whoa, 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 whoa. You're like, yeah! It sucked in extra energy. And then it falls on the ground and it's just shaking and everyone's like, oh no. It blows up. That's the natural progression. Well, it's not like, well, just because. We can explain it now at a more chemical level. There's reasons. Things want to, I shouldn't say that because they don't want anything for their birthday, but if you release energy, you're at a lower energetic state. It's a natural progression. Well, there's other things that we're going to discuss as well. So I thought we could have a little fun first. So, are these going to, oops, I should do that. Are they going to react or not? Well, let's find out. Oh. Let's see if I can do it all at once. Hey. God bless America. As I throw the cooler now. Yay. I had a lot of them in a drawer. I'm like, we're liking these today. There's really no other reason. I was thinking about that, smoke detector. Mr. Machek has always said, if it goes off, it goes off. Keep burning stuff. So, yeah. I'm like, all right. All right. So, that shouldn't have been a surprise, though. Reason why? It was releasing energy, right? But there's more to it. So let's talk about a couple other things. You need to really be sure. When we gain energy, we've called that endo. When we've lost energy, we've called that exo. All right? Units are usually going to be, just so you know, please circle that, because units are going to be problem. Ooh, that smells a little bit. It's going to be in kilojoules, okay? Well, let's talk about this. If it's endothermic, and you were holding it, it actually feels cold. There's a little space below that you can write this in. It feels cold, the endo. If something's exo, it usually feels hot because it's releasing out to you. So what we talked about in thermochem is that means that the heat went to the system, meaning away from you. So it's actually literally taking the heat from your body. That's why you're feeling it maybe that it's cold, or at least it's not coming out towards you. And when you feel it, it's releasing to the surroundings, right? I mean, that's just some stuff that we've learned. Everything right here now on this page so far we've learned. Well, this is the big new thing, and I don't know if this already said that or not. Did it already say disorder?
No, it's nice.
Oh, yeah, right. But so what's the whole point? What does nature normally go to? I just showed you that room. Nature normally, all my cards, we naturally go towards disorder. As we increase disorder, that's when something will usually react. It will usually occur in nature. We are striving to be more disordered. You might have heard the word entropy before. It comes up actually a lot in like Big Bang Theory. Since you've been born, your entropy has increased. And it will continue to increase until you die. Okay? All your organs and everything else is slowly becoming more and more disordered. And that's just the way of things. So we gain entropy as we get older. So let's talk about this term, spontaneous. A lot of you are like, oh, I know what that means. It's instant. Oh, my friend's spontaneous. She dyed her hair the other day. Oh, my neighbor's spontaneous. They go to Vegas randomly. Yes, those are all things with spontaneous. But that is not what it means in science. So speed, it does not mean fast or slow. So a lot of people like spontaneous, like, oh, that's spontaneous. It doesn't mean that, okay? Direction, it's not reversible, so we can't go both directions if spontaneous. What it means is it's going to be naturally occurring. It happens. You're going to read this throughout the packet that, or the worksheets that we have, any reading that you do. It's disorder driven. Nature strives to increase disorder. So, I actually don't feel like I wrote more than that I was supposed to. It's just going to naturally occur. Like you have a boulder on a hill. Maybe it takes 1,000,000 years to get down to the bottom of the hill. But if it does, that was a spontaneous event because it naturally occurred and it happened from the beginning to the end. If a reaction is going to naturally move forward, we consider it spontaneous. We're going to figure out when something is spontaneous and when it isn't. So here is a great example. It's a horrible picture, but a balloon with molecules in it. When you pop it, the molecules spread out. It's a natural event. So that's a spontaneous consequence. It is not when you pop it that they would all stay in nice orderly fashion. Like, oh, we're going to stay right here. Like, it's not like that. And if you're like, oh yeah, but I've seen like those still shots where they have a balloon and water and they shoot a bullet through it and the water stays together. Those are moments, first off, and that's physics of an object in motion tends to stay in motion, and an object at rest tends to stay at rest. It stays at rest for a moment and then it eventually will fall down.
So, like you said, at the boulder, would it still be spontaneous if somebody were to push it down or like increase it?
No, it has to naturally occur. So if you intervene, now if it was going to naturally occur anyway and you intervened on the boulder, it's still spontaneous. But yeah, if you had to do something to it or you have to come into it to make it happen, then that wasn't considered spontaneous. It has to naturally occur. So was that spontaneous? No. But the minute I lit it, the rest of the reaction, it was spontaneous. So now we enter another world of combining things like it has activation energy. Like I can't just wave it around and make it react with the oxygen. I need to add a little energy to do that. Okay? So, but even if it costs energy, here's a great example. Evaporation of water. It naturally occurs, but you have to gain energy. You have to put energy in. It doesn't release energy. What do you mean? The molecules are moving and then they're moving really fast. but yet it's a natural occurrence. From a liquid that's nicely packed together to a gas that's all over the place, that's more disorder. Okay? So this is more disorder by evaporating. If you want, you can write, we have it on the back sheet, but H2O liquid to H2O gas, that's gaining disorder, so that's why that occurs. Even though it's gaining energy. Because on the top part we said that you lose energy. That's what is favored in a reaction. So we're affected by a fine balance between energy, which is change in H, and disorder, which is change in S. And yes, it is very confusing that it is the letter S. And this isn't enthalpy, which is H. It's entropy, which is S. So glad that that's so clear. So let's talk about entropy in general. It means disorder, and that is change in S. It's disorder. Entropy is disorder. It's a really important concept in science in general. So as we gain, when it's a positive, all the other ones, you have a negative H. Hey, that's favored. What else did we talk about in the beginning? Oh, and heat. Well, heat and energy. I mean, you can talk about heat and energy in the same token. You're losing it, it's usually favored. Well, when it's positive, entropy increases. You're increasing entropy. That's good. When it's negative, you're decreasing your disorder. And please circle this, because we will talk about units starting tomorrow. It's a bother, because you have kilojoules in one thing and you have joules in another, and we can't have that. So today's, again, it's trying to get our mind straight on a little bit of what disorder means. Okay, so it'll all come together. All right, so I have we'll come back to the comic. I like the comic on the bottom, the Department of Entropy, but on the back, just to the right side of these, here's are some examples of how we gain disorder. And there's going to be like just questions to you, like why is this favored or not favored? Why is this spontaneous or not spontaneous? If it's gaining disorder, then it's a spontaneous event. It's a spontaneous reaction. It will occur. So this first one, I add particles. All these are adding disorder, by the way. Why? I'm gaining more possibilities. There's more different situations. Just think of statistics. There's more different positions. I'm gaining number of positions. Deck of cards. There's only one way to have it right. There's all these other ways to have it wrong. Okay, so now they can be all rearranged in multiple different ways, and now I've added that even more of a difficulty. This one, what have I done? I've gone from a certain speed for it to even go faster. So there's more possibilities of different positions. So if you add energy, I'm going to keep repeating that about adding number of positions or the different probabilities of a scenario. You're gaining and adding different scenarios and situations and positions. You're adding disorder. What did I do to this one? I increased the volume, space. If I increase space, those particles can be in more different places. Okay, all you got to do is say, okay, can this be exactly this again over here? Well, there's more possibilities for that to be rearranged in a different way. So if you increase volume, you're increasing disorder because those molecules can be in many different, more possible arrangements. This one, I have a certain compound, and what did I do now? I broke it up. So now I have more atoms that are involved. So if you and you could have worded this in many different ways. But if you decompose a molecule, what you're really doing is you're adding particles, like separate particles, right? You're breaking bonds, so you have many more different players in the game of either matching that exact same situation or changing the possibilities, the probabilities. This last one, I tried to word it in a lot of different ways. It said like taking a linear molecule and curling it up. I'm like, well, that's great. Basically, what I thought is you're adding complexity. This is very ordered, and now it's all of a sudden all messed up. Like you're creating a bunch of different scenarios again. Okay, and your job is more to recognize these when they come up. Like, if you haven't already noticed, of all the questions we always have during the year, it kind of states already tells you, hey, this occurs, or this is this situation is happening, explain why, or account for the reason why the disorder increased. Okay, the disorder increased. Let me figure out why. Here are some other ones. They were already on your sheet. They're right belowhand. I just want to say them out loud so we can just practice this. If you have fewer moles or more moles, I'm adding things again. You increase the temperature. Simpler molecules are more complex. We kind of already had that. Did that get dimmer? Ionic solids with strong attractions to ionic solid with weaker attractions. So why, that sounds a little confusing, but if you have weaker attractions, it can break apart easier. So now, again, you have less order. You have more disorder. And then lastly, gas dissolved in water to escaped gas. So you are now not trapped in a liquid. You are now a gas. All right. I thought I had that. We'll jump way down to the bottom for a second. Wait a minute.
We don't know how to find it.
Okay, we're going to jump all the way down, and then we got to come back up. I'm writing on the board for the last part. So here are the laws of thermodynamics. And sometimes this actually shows up a little bit in physics as well. So if you recognize some of this, well, there you go. The reason why I'm bringing this up is that the first law we learned in chapter 6. These next two are kind of what we're talking about right now. It's not your job to recite it word for word, but it helps, okay? So the energy can neither be created nor destroyed. We should know that. The total energy of the universe remains the same. Heat flows from high to low. It always flows from high to low when it's a natural occurrence. These did not gain energy as I lit them. And that's what I'm talking about with the pulse. I didn't light them and boom, 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 boom. It's like, whoa, those are going to be awesome one day. They just keep gaining energy. Things lose energy. We have to intervene somehow, and then that costs energy to do it somehow. So something else is losing energy. But you're always gaining and losing. Second law. Here we go. Then energy systems tend to increase their entropy. Entropy is maximum at equilibrium. Okay, well, we'll talk about that mathematically tomorrow. Okay, and energy systems tend to increase their entropy, so we're increasing disorder. Entropy is maximum at equilibrium. And is that the last thing we have to fill out on that? As temperature approaches absolute zero, the entropy of a system approaches zero. That should make sense, and the reason why is that if absolute zero means that nothing's moving. So you're becoming more and more ordered, because all of a sudden you're not moving, there's no positions that can change. Okay? All right, well, let's find the thing I need. I'm going to go back to that middle section for a second. Oh, you know what? Actually, you have a little space on the bottom underneath third law. Oh, shoot. I was supposed to cover that up. Write these equations. Write these equations one at a time. I want to give you a couple examples of what... Shoot.
Guess you felt hard.
I did. All right. Dang it. These are supposed to be covered. You don't write these really large, but if I went from O2, these are some things that will be on your worksheet. If I go from O2 to 2O, what happens to my entropy? So, and then just jump to the side. Don't keep doing each line. They change in S as positive, and then on the right side of these are the reasons. They're not plus 1 mole. It's plus, like the change in S is positive. I am gaining disorder. Why am I gaining disorder? I went from 1 mole to 2 moles of gas. I'm trying to show you some just real, like, concrete examples that right away you can. What we're going to be doing is looking at equations and going, oh, hey, that's gaining entropy. Hey, that's losing entropy. Right? Oh, there's less disorder there. So that's not going to be favored. Oh, that's gaining disorder. That's going to be favored. So this is favored. Positive is favored. You might even want to write an arrow. Positive is favored. We're gaining disorder. Second one, I have a salt. And it breaks apart into its ions. Positive. And these are too close together. I didn't mean to do it like that. The change in S is positive. So it's gaining disorder. So it's favored. The reason why, it went from a solid to an aqueous solution. There's more disorder there. There's more possibilities for different situations to occur. Okay? And then the last one, I went from liquid to ice, basically. I froze water. That's a negative. That's more ordered or less disorder. Reason why, you're more organized. You're going from a liquid to a solid. You're losing chances for those molecules to be rearranged because once it's a solid, it's kind of locked together. So there's less disorder. There's much more order in a solid than in a liquid or a gas. Okay? So, There's a middle section there, though. I do have to get to that, and then we're going to talk about our worksheet. And you can do quite a bit of it, but not all of it yet.
Isn't it pretty much just, this guy is usually given in joules and then you have to convert it to kilojoules?
Yeah, that's kind of a pain. It's not a huge pain, but it's a pain. All right, sorry, this does not go the way I was hoping for this part of the notes. So it says how to find entropy. That's where I am right now. All right, so this should be on your yellow sheet more or less, but here we go. The entropy of the surroundings, and we're going to make this easier as we go, but I want you to know the real gist of this first, is the heat flow over temperature. And it's less about the math. It breaks it down in more one simple equation, but I can't talk about it until tomorrow because we have to learn this one other thing. So when it's all said and done, sometimes it's just about this. Your total entropy is how much disorder the system has and how much disorder the surroundings have. So let's talk about this in terms. If you have room to go up by the pictures of the three compounds anywhere, I want to talk about the water, ice, and gas. I'm like, what's the other state? I can do this. Let's just talk about this situation right here. I'm just breaking this down so you kind of have an understanding of this. So you should have plenty of space to talk about this a little bit. The system. What am I doing? Let's just talk about signs. This is going to be a positive. And the reason why is that you're going from a liquid to a gas. So again, today my goal is to just give you some big terms and ideas of what's happening. You're increasing the number of particle positions. So that's more what's happening inside is about disorder, like the true positions, okay? The surroundings, this is determined by heat flow. These are like just big ideas. Bring it all together on the worksheet. Right, because the surrounding either gains energy or loses it by transferring of heat. Well, what does that mean? Right here we're doing vaporization. So that's endo. So it's positive change in H. So we'll get into that eventually. We're going to come back to this, but when it's all said and done, the surroundings surroundings lose disorder. Why? Because the energy had to go out from the surroundings into the molecules to speed up the particles. If that makes any sense. So the surroundings actually have less energy around them, so they're not moving as much. So when it's all said and done, what you'd have to know, because if this is positive and that's negative, it's like, well, which one's which? Well, I have this as illustrated as possible here. It matters on the temperature then. If you're greater than 100 degrees, or if you're less. And I know that this is a little confusing right now. I'm just trying to show you, like, you could talk about this without values. Like, wait, why is that? Because if I'm over 100 degrees, I'm boiling. So now this is going to engage itself. If I'm below 100 degrees, then it will not be boiling, so then I'm not gaining as much order when it's all said and done. You're like, well, why didn't you just start that in the beginning? Because you might have to break it down. But the overall process, it will be engaged if it's positive, if it's over 100 degrees, boom, then we're going to have this. Well, then we have to then that will relate this sign. If it's below 100 degrees, that means it will not be boiling. So then we're going to have a negative entropy, meaning that we're not going to be more disordered, or we're going to have less disorder, more order.
So is it going to be in Kelvin for the surroundings then?
Yeah, but yes, but we're not really going to do a lot of those calculations. So let's take out our worksheet. Let's bring this home.
What does UN mean?
Universe. Let's bring it all together. So, let's talk about this. First off, just so you know, anything that talks about a G, you don't do right now. So just know that. Don't cross it out. But anything with a G, you don't do. But for the most part, and it's not gravity. So like number 6, it says something about change in G. Don't worry about it then. If you feel like we didn't cover something, we'll all bring it back together tomorrow, okay? But you don't necessarily have to do the math right now. What I would do is look for things that talk about relationships. So here's an example. Number 1. Which of the following represents an increase in entropy? So you could take the long route and explain each of those. You could do, my answer here, I believe, I have little parentheses just saying something really short, like more ordered or less particles. But then I explain the one. So we can do this one together. These are kinds of questions that you're really going to be responsible for. Which one has an increase in entropy? Freezing of water, boiling of water, crystallization of a salt. The reaction of that or the reaction of that one. So what if I asked for all the different reasons? I want to just talk about it. So like letter E. Is that an increase in entropy? It's no, because I went from 3 moles to 2 moles, right? Like I'm going to use this as a teaching tool. So what I would for you, if I were you, just for the sake of this, just put a parenthesis next to each of these quickly just to kind of explain. So there's 3 mole arrow to 2 moles. Like it's less. Letter D, same idea, right? It went from 2 to 1. So there's more order. There's less disorder. It's always very confusing. Like, which one do I say? Try to say disorder as much as we can. What about letter C? Is that gaining entropy? Crystallization of a salt from a supersaturated solution, meaning that you had a salt in solution, and what it did is it crystallized it, so it became a solid from AQ. More order, right? It became more structured. There's more order. It went from AQ to S. Right? There's more order there. So it comes down to the last 2. I mean, you could write parentheses in each one. Freezing water goes from a liquid to a solid, right? And boiling water goes from a liquid to a gas. And I know it's kind of, well, you kind of just did one. Yep. So it should be B, because you're gaining more disorder, but you can't just say I'm gaining more disorder. When it asks for which one has increasing entropy, the word entropy means disorder, so you can't be like, well, that's gaining disorder. So you have to talk about something else. What I would do is, what I just wrote here, it's increasing the number of particle positions, okay? Or the particles are moving much faster, creating more possibilities. Or arrangements, that's another word. Trying to give you some different ammo if you feel like you're repeating the same words all the time. So, like number 4, I'm not going to say it out loud, like the whole thing, but in which of the following reactions do you expect to have a decrease in entropy? Okay, so that now leads us down to that path. So which one would have a decrease in entropy? So you have to look at states and you have to look at moles. You have to kind of think about that. Okay? Obviously, if you have solids versus gases, gases have more disorder, but it's the before and the after. So you're going to have to be a little selective. Unfortunately, there's a lot that, now that I'm looking at it, because all the math I have to quickly throw out to you tomorrow. And the math is actually really simple to do. You know what? I'll help you right now so you can calculate this one. Number 3, you do final minus initial with multiplying them by moles. So take the amount, if you can hear what I'm kind of saying, like we've done this a little bit before. It's the change in S. So it's the amount of entropy at the end minus the amount of entropy in the beginning. But you got to factor that out. So what would you do with the oxygen value? You multiply by half because those are all per mole. Right? So it's the sum of the products minus the sum of the reactants. Okay, so, shoot, I knew we wouldn't have enough time to get into the exact specifics of the math, so I wouldn't stress out too much. Make sure you have number 4 answered, try to do number 3 if you can, and then all this will kind of come together because all we have left is one letter. Like, what the heck is G? You get an equation that's on your yellow sheet, and you're just going to use it. Okay, and we just apply it. So, disorder, things are favored when we gain more disorder or when we release heat. And disorder is about gaining possibilities, positions, arrangements, however you want to view it, okay? Lastly, if you have not yet, you should have had 3 things handed in the last couple days. Acid basis 3, the titration packet, and lesson 21. If you haven't yet, I'll tell you now, I did not collect